We are now beginning Chapter 9. Chapter 9 talks about radiation, nuclear radiation. In the first section, we're just going to have a little introduction into natural radioactivity. A radioactive isotope has an unstable nucleus. Now let's take a small refresher on that. The nucleus are the protons and the neutrons in the middle of the atom. Surrounding the nucleus are the electrons. Up until now, we've been talking about the electrons on the outside. This time, we're talking about the center of the atom, the protons and neutrons. Radioactive isotopes emit radiation to become more stable, changing the composition of the nucleus. Now, if we look at the periodic table and we go to atomic number 19, there's a trend that essentially the protons are about the same as the neutrons, and those are more stable. Once you get beyond that, it becomes less and less stable. Once those protons aren't equal as well to the neutrons, it becomes less and less stable, and so the atom is going to try to react in order to make it more stable again. So the isotope is identified by the mass number, which, if you don't remember that, the mass number are the protons and the neutrons added together. The element is identified by the atomic number, which is just the protons. The atomic number is what you're going to find on the periodic table, where the mass number is for a specific isotope. The number that you see that's rounded off on the periodic table, so if we look at the periodic table, and let's say we're looking at calcium, and it's 20 and 40.08. This number here are the protons. That's the atomic number. This is the atomic mass. Do not confuse that with the mass number. They are two different things. A mass number is for a specific isotope. Atomic mass is for all the isotopes averaged together. That is extremely important. So here are the main radioactive particles that we're going to be dealing with. Alpha, beta, positron, gamma, proton, and neutron. These are all things that are found inside the nucleus, in the center of the atom. The alpha particle is the biggest, with the mass number of 4, which means the protons and the neutrons added together is 4. And this down here are the protons. So the protons are 2, which means the neutrons must be 2. And it has a charge of a +2. The beta particle is a neutron and an electron emitted. It's an electron. It's extremely small. The weight of it is so small, they actually put 0 down. Same with the positron. They put 0 down because the weight is so small. These two are opposites of each other. Beta particle is negative, positron is positive. A gamma ray is if those two particles come together and collide, and it's going to give off energy. And that's the gamma ray. Notice the positive one and negative one cancel each other out. That's why there's no change here. It's just energy. Then the proton and the neutron are what we already know about from our experiences with the atom. Those are the bigger particles that are inside the nucleus. So, the types of radiation again. Alpha particle. They give a symbol of He. It could be He or alpha because of the fact that there's 2 protons. And so, if you look in the periodic table, the atomic number for helium is 2. And so that's why they give it that symbol. Beta and positron are the opposites of each other, electrons. Beta is negative, positron is positive. Neither one have a mass because it's so much lighter than anything else. And then those two coming together will form the gamma. There are certain precautions that you need to make as far as radiation poisoning. And as nurses, you're going to need to know that just simply because you will deal with radiation. Like when you're doing x-rays and whatnot. But the protection depends on the particle we're dealing with. So alpha, beta, gamma. In general, however, you want to limit the amount of time you spend with the radioactive source. And you want to get as far away from it as possible. But we're going to talk about these differences here on the next slide. If we look at the particles next to each other and we do a comparison, the alpha particle is the largest, where the gamma ray is the smallest. If you think about it in terms of a ball. Let's say that the largest maybe is a bowling ball, while the beta is a baseball. And then the gamma is like a golf ball. The differences in the sizes and the weights make it really hard, give you the differences in how far it'll travel, how well it'll hit something, so on and so forth. For instance, a bowling ball is really hard. It's really heavy. It's really hard to throw. An alpha particle is really big in comparison. It can only go 2 to 4 centimeters. Whereas a baseball, it's still heavy, but it's a lot smaller, easier to handle. It can go 2 to 300 centimeters. And then a golf ball being the smallest is the easiest to travel. Like the gamma rays, it goes 500 meters. Notice the difference in meters, centimeters to meters. That's a huge difference. So if we put this into centimeters terms, 50,000 centimeters. Notice that leap. And it's all because of the changes in size. So because of that, when we're looking at ways to protect ourselves, the alpha particles can be protected with clothing or a piece of paper. If we're looking at beta particles, you're going to need something a little bit more substantial. And gamma rays are the most dangerous, and you'll need like a lead coat or a thick concrete to protect yourselves. And that is the end of the introduction for nuclear radiation.